Hey guys, welcome to the next video. So this one is going to be focusing on something called the Birch Reduction, as well as two oxidation reactions that you guys should be familiar with that can help you out when you're doing electrophilic aromatic substitution reactions. All right, so the first one we're going to focus on is the Birch Reduction, and these are going to be the reagents you want to use. All right, so I'm going to start off with just showing the example with benzene, and then we'll see what happens when we have different substituents on it. All right, so here's these reagents. So what is going to be the first step in the Birch reduction? So I'm going to redraw this over here. Now this sodium has a radical on it. Yeah, we're back to radicals. All right. So the first thing that happens is it's going to react. And actually, let me just, for ease, shift the double bonds over. One of these radicals one of the electrons in this double bond, right, reacts with that radical, the electron from the sodium, and then the other one is going to come over there onto one of those carbons in the form of the other radical, right? Because remember, there are two electrons for every double bond, so one of these is going to the sodium electron, the other one is going off on its own. So what that's going to give us is this. We put the radical up here, nothing happened to these double bonds, and since we combined those two electrons, we get a lone pair right there, right? So there's two electrons there now, and that's going to put a lone pair on that carbon. All right. Now all I'm going to do is I'm just going to shift over that lone pair, resonate it this way, and take this double bond, because remember octet rule, and put it on this carbon in the form of a lone pair, giving us this. Radical there, double bond there, new double bond here, and that lone pair over here. Okay? And so this is what we have so far at this moment. Now what's going to happen, and actually what I'm going to do is I'm just going to rotate this just to make it easier. All right. So now what's going to happen is we have this ETOH, right? This is just this compound. So it's this ethyl group with this alcohol on it. And that lone pair is just going to grab one of the H's. And remember, there's already a hydrogen on it, right? All these carbons on benzene have a hydrogen unless there's something else is shown. So that's going to grab that hydrogen. The lone pair goes onto this. So what happens is we neutralize that lone pair, that negative charge. So that's going to be neutral now. And we still have this radical here. Now what happens is another sodium radical is going to react with with our existing radical. And so because those two electrons combine, we now have a lone pair there. All right, here's that negative. And again, we react with one of our ETOH molecules. Tag that H. It breaks off, and we get this compound now. All right. So this is the Birch reduction. Now, why is this important? What is this going to help us with? So it's useful when we're dealing with, when we have something on the benzene right here. So if I drew, let me fix this over here. So if I drew this compound, right, and let's say I put this OCH3 group on. How is this going to affect what happens to our compound? Right? So let's see. We're going to have our sodium, right? So remember what happens with our sodium? It's going to react with one of the double bonds, correct? And so let's use this one. Doesn't matter which one. This. And now the lone pair, I'll put the other radical over here. So what's going to happen is we have this OCH3 here, lone pair over here, and the radical right there. Okay? Doesn't matter where you put them. Now, let's resonate that negative charge. This guy comes over here, and now this one moves over there. So we can see what happens is now we have this. Negative is on this carbon, the radical is here. We can see that we have this negative charge on a carbon with this OCH3. Now, OCH3, remember that oxygen has lone pairs, so it can function as an electron donating group. So it prefers to put electrons downwards into the ring, but we already have a negative charge there. So when we have we have an electron donating group next to an electron rich atom, that's not favorable. That's going to be unstable. All right. And so what's going to happen is we're going to prefer to not have that negative charge there. So what we want to do is we want to essentially move that negative charge instead. All right. So we're going to position it some other way. So what I'm going to do instead is I'm going to, let's say, move it across, or actually let's just focus back on what we have here. All right, when we're back to this guy. In this reaction mechanism, you always want to have the radical and the negative charge opposite each other. So when we do this step, when we're neutralizing the negative charges, you must have the radical and negative charge opposite each other. So in this case, I put the negative on the carbon with the OCH3, and so you can see that that radical is opposite, right, on the opposite side. So what I'm going to do is I'm just going to use this guy because the negative charge is right there. And so I'll just move the radical over. So what's going to happen is this radical, let me erase these arrows actually, comes here. One of the electrons from the bond also moves over there, and then one of the electrons comes over there. If you're a little bit rusty on how we move electrons and radicals, I suggest you go back to the previous videos I made when we first learned radicals. OCH3 is here. Alright. And now what happens, this double bond stays. A new radical is over here, and we formed a new double bond there, and our negative charge was right there. Now we can go through the neutralization steps because you can see that the negative charge is not on the carbon with the OCH3, which is good, right? We don't want that destabilizing effect. So we're going to grab this H. This guy gets deprotonated. He's neutral now. We have this radical now. Again, we're going to have this Na radical react, and it's going to be the same exact process that we did here. We're going to form a negative charge, and then we deprotonate again. So I'm just going to skip ahead. So the final product is going to look like this. This is the final reduction product. All right. Now when we have, and this is when we had an electron donating group. All right. So when you have an electron donating group, your double bonds must be essentially, you must have it on the carbon with the OCH3. You don't want it like this. So if you had that donating group, you do not want this guy. You want it to look like this. All right. Now, what about if we have a withdrawing group? Let's take a look at that. An example we can do is this right here. This ketone, right? So this is a withdrawing group. Now, if we do the Birch reduction, so here's our Na radical. It's going to react to double bond, right? And we're going to put that radical there. Doesn't really matter. And so what's going to happen is now these two double bonds remain the same. Negative charge on this carbon, radical on this. Now we want to get them opposite each other. So what I'm going to do is I'm going to resonate this guy this way. And put the negative, use this double bond to put the negative charge on that carbon. With double bonds this way now, parallel to each other. The radical is here, and the negative charge is now here. All right. Now, this one, remember how when we had it like this with an electron donator group, this was not good, right? But in this case, we have an electron withdrawing group, right? Remember, this ketone is a withdrawing group because I can resonate this over here, and I'll have this sort of structure. O minus, positive charge, negative charge. So that positive and negative charge, they can kind of stabilize each other, right? Because I can now take the negative charge, resonate him this way, and have this. Right? So they stabilize each other. So having that negative charge on the carbon with the withdrawing group is better in this case. It is actually what we want. All right? Whereas when we had an electron donating group, we didn't want that. So in this case, we're good. We're all lined up and ready. All we got to do now is take our HO and then our ETOH, start deprotonating him to neutralize. So that's neutral now. We saw this radical. And then again, we repeat. We'll react with another Na radical like this. Right, to get the negative charge, then we neutralize again. So when you have a withdrawing group, what you want is for those to be lined up right, like this way. So electron withdrawing group. So these are going to be the overall results of your Birch reduction. All right. So note the patterns, but it's a good idea to know the mechanism. All right. And also, obviously, make sure you have the proper reagents down. Right, we don't want to get points off on a synthesis question by not writing down a certain reagent. So that's going to be the end of the Birch reduction. All right. So now we're going to focus on oxidations. All right. So I'm going to just erase this. All right. So these are good and useful reactions for synthesis, and they could come up in other questions like multiple choice and short answer. All right. So we're going to talk about now oxidations, and specifically we're going to talk about oxidations obviously in the context of electrophilic aromatic substitution, but mainly in the context of when we're looking at the benzylic position. So that's the carbon right here. That's the benzylic carbon. Right? So I'm going to give some examples. So there's two oxidation reagents. One of them is much more common. Right? And you'll probably see the only reason I bring up the other one that's less common is because it was given in lecture when I took this class, and you could always just put it on your index card if you have it, if you're worried, and it's just another thing you could use in synthesis. So the first one is called KMnO4. All right, and that's all you need to write. All it does is it's a weak oxidizing agent. All it does is it will take a alcohol on your benzylic carbon, so it's got to be this one, and it turns it into a carbonyl. That's all it does. So you can think of it almost as PCC, but this one focuses exclusively on the benzoic position. So this alcohol over here is not touched, right? So if we use PCC, we would have had both of them turn into carbonyls. All right. So it's a useful reagent. Now, that's the weak oxidizing agent. There is a stronger oxidizing agent. All right. So let's see what we have here. That could be a stronger oxidizing agent. Oh, and also one other thing. If you have this sort of compound, so not to benzene, but you have this alcohol that is exactly, if I count them, 1, 2 away from a pi bond, you can also use this on it. Right, and that can come up like this. All right, now that's like a really rare case. I've never seen that come up before. It was only shown in lecture one time, so don't focus too much on this thing. Right. So those are the weak oxidizing agents, MnO2. The next one is going to be a stronger oxidizing agent. All right, and this is going to have to be written in steps. So what I'll do is I'll show the same exact reagent before. Oh, my bad. So this is going to be step 1, KMnO4 OH minus and heat. Step 2, H3O plus. Alright? And so this is a much, much stronger oxidizing agent. And what's going to happen is it's going to react specifically with a benzylic hydrogen, alright, or pi bonds, either one of them. So right here we have a hydrogen, the benzylic hydrogen. You don't need to know the mechanism for this. And what it's going to do is it's strong enough that it's going to immediately take everything to carboxylic acids. So what's going to happen, rather than just stop at the carbonyl, it's going to keep everything here. That's the weak oxidizing agent. It's going to cut everything off of here and create this carboxylic acid. All right, so that's what this does. And it's with any benzylic hydrogen or a pi bond. So let's say I had this right here, a methyl, that works because there's 3 hydrogens here, right? And they're at the benzylic position, so you immediately get this. All right. Doing this guy, same result. Benzylic hydrogen, right there. How about this guy? That was horrible. Oh man. All right, there we go. So that guy, he doesn't have a benzylic hydrogen, but there is a pi bond at the benzylic position, right? That pi bond is connected to that one carbon right there, that benzylic carbon, so he counts, right? And that will create the same exact product, all right? Even this guy, all right? Remember, triple bonds are composed of 1 sigma and 2 pi bonds, and he's at the benzylic position. Remember, when we count carbons of alkynes, that's 1, that's 2, that's 3. That's good, and he's going to create the same exact product, right? And even this guy works. If you have this, right, this is a pi bond, so same product. This one, on the other hand, though, this one will not work. Tert-butyl, right, there's no benzylic hydrogen here, there's no pi bond. So this guy will not create that carboxylic acid, all right? So like here, let's do an example question. So if I had this structure, and we react with KMnO4 OH minus and heat, which I'll just write as a triangle, and you have to number that. That's step 1. Step 2 is some acid, or just H3O plus. All right. What would be the product of this? And I'm just going to do it down below. Well, let's see. We always look at the benzylic carbon in this case, so that's this carbon, and don't forget this guy. All right, so he has benzylic hydrogens, and so does he. So both of them will be oxidized, and both of them will be carboxylic acids. And remember, it cuts off pretty much everything. So that means the rest of the chain doesn't matter. We just draw carboxylic acid and call it a day. All right, and same here. All right, and that's would be your answer. That would be your answer, all right? That's all you get, all right? So hopefully not too bad. I know the Birch reduction mechanism could be a little bit tricky, but you always have your index card, and there's always the patterns that you can write down. But again, I still would be familiar with the mechanism. Good news about the oxidations is you don't need to know the mechanism, all right? Now the KMnO2 stuff, that was really just shown in lecture. I've never seen that come up in an exam or on a workshop or anything. But KMnO4, 100% it's come up. All right. So I hope this video helped, and I'll see you guys in the next one.